Okay, so the next chapter that we're going to cover is chapter 20, which covers electrochemistry. And a big component of this electrochemistry chapter is going to be redox, the oxidation and reduction reactions that we looked at a little bit in earlier chapters, but we're going to cover it much more fully here. Okay, so one thing that you want to do before you get into this chapter is go back to chapter 5 and look at the list of oxidation state rules for the assigning of oxidation states, because we're going to need those throughout this chapter. If you look on your Pearson shared documents, I posted that list of rules again. Professor Sheehan also has them in the handouts that you were given in class. But you want to refresh your memory on the redox rules for the oxidation state assignment before you jump into the balancing the flow redox equations, or else some of this won't make very much sense. Okay. We're going to start with these questions here, which are balancing the redox reactions in acidic solution. Okay, you're going to be told whether you're balancing the reactions in acidic or basic solution because it's going to affect one of the steps in the balancing process. This should become a little more clear as we go through the examples. Before we actually start balancing though, take a minute to write down the reactions that we're going to be working with, and also take a minute to write down the steps. I'm going to be referring back to these steps while I balance these equations, but it's good if you have these written out for yourself, because then it's going to help you remember them a little bit better. If you are adamant that you don't want to write it down, at least get a picture of it so you can reference it when you're going through the redox steps on your own. But there's no, I don't know, there's nothing better than actually writing it out for yourself, because that's how you're going to actually make yourself retain the information. Step by step going through the balancing process, you'll see that the first step is going to be to assign oxidation states to every atom that's in the reaction so that we can identify what is being oxidized and what's being reduced. Okay. Once we figure that out, we're going to split the overall reaction into what we'll call two half reactions. One half reaction will represent oxidation and the other will represent reduction. Then we're going to start our balancing process, and we're going to balance one reaction at a time. Doesn't matter which one you do first, you just have to balance one at a time. And when we're balancing these, we have to balance in this particular order. Okay, so the first thing we're going to do is we're going to balance any element in the half reaction that is not hydrogen or oxygen. Okay, we have to make sure that that is balanced. When that's finished, then we're going to balance any oxygen discrepancies by adding water molecules to whatever side is missing oxygen. All right. Then after that, usually by adding water molecules, we disrupt the hydrogen balance. So to fix the hydrogen imbalance that happens, we're going to balance that hydrogen by adding hydrogen ions to whatever side is missing hydrogen ions. All right, and once we do that, then our atom balancing is finished. And then we're going to move on to balancing the charge. Okay, so to balance the charge, we're going to look at the reactant side, and we're going to add up the charge on the reactant side, and then we're going to add up the charge on the product side, and we'll compare them. If there's a charge difference, there will be, you're going to add electrons to the more positive charge side until both charges are the same charge. Okay, so for example, if my reaction looked like this, like I have reactions versus products, or reactions form products. If the charge on my reactant side was, let's say, -2, and the reaction on my product side was +4, okay? I have to look at my product side and say, well, I'm going to need to add as many electrons as it takes for the charge on this side to get to -2. Okay, so to do that, I would have to add 6 electrons to the product side so that when I looked at the total charge on the product side, it had the same charge as my reactant side. The next step is going to be to, it doesn't actually say this, but I guess it should be like step 4.5, is that at that point, once you get to step 4, in one reaction, you have to go back and repeat those 4 steps for the next reaction. Okay, and the next reaction, I mean that second half reaction. So if you did your oxidation half reaction first, once you finish step 4, you have to go and repeat steps 1 through 4 for your reduction half reaction. Because to do step 5, you need to have 2 balanced half reactions. And then at this step, you're going to have to make the number of electrons in both of those balanced half reactions equal by multiplying one or both of the reactions by an integer, okay, a small whole number. So if you have 3 electrons in the oxidation half reaction and you have 2 electrons in your reduction half reaction, you'll have to multiply oxidation by 2, so you end up with 6 electrons, and the reduction by 3, so you end up with 6 electrons. Hopefully I said that right. But 2 times 3 is 6. So you have to multiply by the number that will give you the same amount of electrons in both your oxidation and reduction half reaction. Okay, and that's important because when we get to step 6, we're going to add the 2 half reactions together. And this is going to let us cancel out the electrons as well as any other species that we're able to cancel out. To decide what can be canceled out, we're going to look at the reaction arrows, okay? Species that are on opposite sides of the reaction arrow, those species are going to cancel out. And your electrons should always be on opposite sides of the reaction arrows, or else something went wrong in your balancing process. Okay, so if you have electrons on the reactant side and electrons on the product side, those should cancel out. But if you had water on your reactant side and water on your product side, that would also cancel out. Okay, if you have species that are the same on the same side of the reaction arrows, those will add together. So if you had hydrogen on your reactant side, not on your reactant side, on the reactant side of your oxidation and on the reactant side of your reduction, those would add together. I think I said reactant and product when I did my last example. So just what I mean when I'm talking about them being on opposite sides of the arrows, we're going to have an oxidation half reaction and a reduction half reaction. So things that are on opposite sides would be on opposite sides of those reactions. Like your oxidation might have water on the reactant side, but your reduction would have water on the product side. That's when cancellation would happen. If your oxidation has water on the reactant side and your reduction has water on the reactant side as well, those would add together. Okay, but we'll go through the examples of this now. Okay, sometimes it's easier to see when you're actually going through the process. So let me pause this a minute and write down the reactions. Okay, so this is going to be our first reaction, and we're just going to go through step by step to balance these out. Okay, so step 1 is to assign oxidation states to everything. Our free elements, which are going to be aluminum and copper metal, right? These are both neutral. These are both going to have oxidation states of 0. Copper ion and aluminum ion are both monoatomic ions, so they'll have the same oxidation number as their charges. Okay, then we can figure out oxidation and reduction by looking at the change in oxidation state. See, we went from 0 to +3. That's an increase in oxidation number, so that's oxidation. Copper went from +2 to 0. That's a decrease in oxidation state. That's reduction. Now that we have our half reactions identified, we're going to be able to split them up into the half reactions. So just do it like this. So our oxidation half reaction is going to be Al solid leads to Al3 plus aqueous. And our reduction is going to be Cu2 plus aqueous leads to Cu solid. Okay, and what you're going to notice when you split these up into their two half reactions is that when you go through the process of balancing these half reactions, your oxidation half reactions are always going to have electrons as products, right? Because losing electrons means oxidation. And your reduction half reactions are always going to have electrons as reactants. All right. Now, the first two examples are very simplified ones. There are no other types of atoms in the reaction. So this is going to move a lot faster than normal redox stuff. Here, our aluminum atoms are balanced. So the first part of step 3 is finished. There are no oxygens and there are no hydrogens. So the other parts of step 3 are also completed. We're going to move right into step 4, balancing the half reactions with respect to charge. So aluminum obviously has a 0 charge, and aluminum ion has a +3 charge. So I'm going to add 3 electrons to the product side so that the overall charge of the product side is the same as the reactant side. Okay, so now if I added the charge of my product side together, I have +3 plus 3 electrons. That's a total charge of 0. Okay, now I'm going to do the same thing over here. I have a +2 charge for my copper, and I have a 0 charge, or +2 for my copper ion, and a 0 charge for my copper solid. So I'm going to add 2 electrons to my reactant side, so I get the same charge as my product side. Okay. Now I'm going to be up to step 5. And step 5 is when I'm going to make the number of electrons in both half reactions equal by multiplying one or both by a small whole number. So I have to make the number of electrons in my oxidation half reaction and the number of electrons in my reduction half reaction the same. Right? So when you see 3 electrons and 2 electrons, the common number between them is going to be 6. So I'm going to erase these charge tallies because I don't need them anymore. I'm going to take this entire half reaction, my oxidation half reaction, I'm going to multiply the whole thing by 2. So now I'm going to end up with 2 aluminum solids, gives me 2 aluminum ions, plus 6 electrons. And I multiply this entire half reaction by 3. 3 times 2 is going to be 6 electrons plus 3 copper ions gives me 3 solid copper atoms. Okay. Now step 5 is done because my electron numbers are the same. So step 6 is going to be to add these reactions together. So I'm going to rewrite them so they look a little more like almost like a math equation. Let's write that a little further over. Okay, so now I'm going to add these two things together. So I like to draw my little line between the reactant side and the product side. And I'm going to focus in here on these electron values first. They're on opposite sides of this reaction arrow. So they're going to cancel out, and we want them to cancel out completely. We never want leftover electrons. That's why we go through this step where we multiply like that. Okay. So those cancel out. I can't cancel out anything else because nothing else appears in both sides of the reaction. All right, so I'm just going to pull down everything else. And I end up with 2 solid aluminum plus 3 copper ions. Gives me 2 aluminum ions plus 3 copper solids. And that is going to be my balanced redox reaction. Okay. So we are going to try the next one. Put it back up on the screen for a minute if you need it again. We're doing number 2 now. Number 2 is going to be another one that moves kind of quickly because we don't have a lot of extra types of atoms in there. Once we start seeing oxygens pop up, but like in these last 2 examples, those are going to be the interesting ones. All right. So I'm going to pause this and write out the next reaction. Okay, so here's the next reaction. And we're going to start by assigning oxidation states to everything. So our monoatomic ion gets a +1. Our neutral atom gets a 0. Our elemental hydrogen gets a 0. And our chromium ion gets a +2. So we're going +1 to 0, that's reduction. 0 to +2 is oxidation. Okay, so I'll put my oxidation over here and my reduction over here. Why not? And like I said before, this is going to be another one that is not very complicated because we don't have a lot of extra atoms in here to kind of mess it up. Okay, so we're going to start by noticing that the atoms here are balanced. We have 1 chromium in each one. There's no hydrogen or oxygen. So we're just going to have to balance this half reaction by charge. Our chromium has a 0 charge. Our chromium 2+ has a +2 charge. So I'm going to add 2 electrons over here to make our charges equal. Okay, when I come over here, the only elements that are in this half reaction are hydrogen. So I'm going to need to add another hydrogen ion to this side to make my hydrogens equal. Right? Now I have a +2 charge over here, and I have a 0 charge over here. So I'm going to need to add 2 electrons to my reactant side to make my charges 0 on both sides. Okay. This particular reaction is even quicker now because my number of electrons is the same on both sides. So I'm just going to add these together, right? So I'm just going to rewrite my reduction. This was confusing the way that this ended up being written out. This is my oxidation. This is my reduction. I'm going to just take my reduction and put it over here so I can add them together. Okay, so I see again that my electrons are on opposite sides, so they're going to cancel. Everything else is going to stay in the reaction and it's going to come down for my overall reaction, which will be chromium solid plus 2 hydrogen ions. Oh, and those hydrogen ions are aqueous. Gives me chromium 2+ aqueous plus H2 gas. Okay. Now we'll do one that's a little more interesting that actually has to use more of the steps. So that's going to be reaction 3 here. And this one should look familiar to you because it's the same reaction that pops up in your permanganate lab, right? This reaction 3, and I know that you're asked to balance this reaction for lab, so hopefully you've seen this before. Okay, so there's our third reaction that we're going to look at, and we're going to start again by assigning oxidation states to everything so that we can figure out where our oxidation reduction is. Hold on, I made a typo. That's what I call it, even when I'm just writing, it's still a typo. That's just a 2 plus. So we're going to start by writing out our oxidation states. Iron's +2 here, and it's +3 on the product side. The manganese ion is going to be +2 over here. And in the MnO4 minus, each oxygen is going to have a -2 oxidation. So the total contribution from oxygen is going to be a -8. The oxidation state of manganese and oxygen has to add together to be -1. That means the oxidation of manganese has to be a +7. Okay. So that being said, we can figure out where the oxidation and the reduction is happening by looking at the iron and the manganese. So iron goes from Fe2 plus to Fe3 plus. So that's going to be oxidation. The manganese goes from a +7 to a +2. That's a decrease in oxidation. So that's going to be reduction. Okay, so now we're going to split these up into the half reactions. Our oxidation half reaction is going to be Fe2 plus to Fe3 plus. Our reduction half reaction is going to be the rest of it, our MnO4 minus to Mn2 plus. Okay, so we're going to start by balancing anything that is not hydrogen or oxygen. Our irons are balanced in this case. Our manganese is balanced in this case. So we're going to focus on the hydrogen and the oxygen first. There are none here, so we can skip that step. We can go right to our electron step. So we have a charge of +2 here and a charge of +3 here. So I'm going to have to add 1 electron to my product side to make the charges on the reactant and product side the same. Okay. So now my oxidation half reaction is ready to go to finish my reduction reaction now. I'm going to balance my oxygens first. Okay, I have 4 oxygens here. I have 0 oxygens here. So I'm going to add 4 water molecules to my product side. Okay. When I do this, now I have 4 oxygens, and my oxygens are the same. When I added the 4 water molecules, though, I messed up my hydrogen balance. Now I have 8 hydrogens on my product side, and I have 0 hydrogens on my reactant side. So I'm going to fix that by adding 8 hydrogen ions over here. Okay, so that's how that works. Now, I'm going to need a little more room. Now I'm going to look at the charge difference because all of my atoms are balanced, but my charge situation is a little bit of a mess still. I have 8 hydrogen ions, so each hydrogen has a +1 charge, and I have a manganese with a -1 charge. So I have a total charge on my reactant side here of +7. Water is neutral, and I have 1 Mn2 plus ion, so my charge here is +2. Okay, so I have a difference here between these two of 5 electrons. Sorry, 5 electrons. So I'm going to have to add the electrons to the more positive side so I can bring this +7 charge down so it's +2. So we're going to put them over here. Okay. Now we're looking at step 5. We have to make the number of electrons equal in both half reactions. In this case, the easiest thing to do is going to be to take my oxidation half reaction and multiply the whole thing by 5. And then when I do that, this oxidation half reaction will have 5 electrons, and the reduction one will as well. Okay, and now I can take these two half reactions and add them together. Okay. Oh, I keep writing 3 plus over here instead of 2 plus. I don't know why. Okay, so now we're going to look and we're going to cancel things out that fall on opposite sides of the arrows. I've got 5 electrons here and 5 electrons here. Those cancel. Nothing else cancels out here, so everything else is going to come down. Right, so I have an overall reaction of 5 Fe2 plus aqueous plus 8 H plus aqueous plus MnO4 minus aqueous yields 5 Fe3 plus aqueous plus Mn2 plus aqueous plus H2O liquid. And that's going to be our overall reaction. Yeah, that should be a little liquid over there, but okay. And this is our balanced equation. So we see that we have like 5 moles of the iron ion for every 1 mole of the permanganate ion, which is, if you remember back to your lab, that's the relationship that you used to solve for your percent iron in that lab, right? Okay, so we're going to look at the last reaction now. Let me put it back up real quick before. Okay, so let's write that one down and try this one out. Okay, so here's our last reaction that's going to be in acidic solution. Then we'll move on to doing some basic solution examples. I'm going to start again by assigning oxidation states so we can separate out the reactions. Oh. Okay, so hopefully we see how that went. We went from 0 to +2 with the copper, that's oxidation. We went from +5 to +4 for the nitrogen, that's reduction. Our oxygen just stayed at -2. So we'll do the oxidation half reaction first. That one's going to be quicker because there is no step 3 here, right? There's no atom imbalance here. The only thing that's imbalanced is the charge. It's 0 here, it's +2 here. So we're going to add 2 electrons here to balance out that charge. Okay, and now we'll do our reduction half. So our nitrogens are balanced. We can move on to balancing the oxygens. We have 3 oxygens here and we have 2 here. So I'm going to add 1 water here. so that now we have 3 oxygens on both sides. Now we'll move on to the hydrogens. I've got 2 hydrogens here and I've got 0 here. So I'm going to add 2 hydrogens, 2 hydrogen ions. Okay, now I'm going to look at the charge difference. I've got 2 neutral species here, so my total charge is a 0. I've got a positive 2 charge because I have 2 hydrogen ions and a negative 1 charge for my nitrate ion, so my total charge here is positive 1. So I am going to be adding 1 electron here, so that my total charge, 1 electron, 2 hydrogen ions, 1 nitrate ion, equals 0, right? But now I have to make these electron values the same. So to do that, I'm going to take this entire half reaction and multiply it by 2. And I'm going to write the product down here. Okay, so I'm going to end up with 2 electrons plus 2 times 2 is 4 hydrogen ions plus 2 nitrate ions gives me 2 NO2 gases and 2 H2Os. All right, and now I'm going to bring my oxidation half reaction underneath it. And I'll add them together. So my electrons are going to cancel out. We're going to see a lot more cancellation happening when we get to the basic half reactions in a minute. I'm going to put the copper over here because I'm going to run out of space. Obviously, the order of these doesn't matter as long as the correct species are on the reactant side and the correct species are on the product side. Okay, and that's going to be our balanced overall reaction. Okay. Now we're going to move on to the basic half reactions. Okay, and what I want you to note as a difference in the basic half reactions is what's going to happen in step 3. Okay, now there's more than one way to balance these basic oxidation reduction reactions. I'm pretty sure that in the notes that Professor Xian gave you, that recommends that you wait until the final step to get rid of the excess hydrogen ions. That's fine. But the way that your textbook presents it and the way I'm going to present it to you is after we go through the other parts of step 3, after we balance all of our elements, after we balance the oxygen with water and balance the hydrogen with hydrogen ions, after this step, we're going to say to ourselves, well, I'm in a basic solution. Basic solutions aren't going to have hydrogen ions just floating around in them because they're basic solutions. So at this point, we're going to neutralize the hydrogen ions by adding hydroxide ions to both sides of our reaction. We're going to add exactly as many hydroxide ions as we have hydrogen ions, okay, to both sides. The reaction that has the hydrogen ions, or the side of the reaction rather, that has the hydrogen ions on it, is going to end up with that many water molecules because hydrogen plus hydroxide is going to give us water. And the other side of the reaction will end up with our hydroxide ion, which represents a basic reaction. All right, it's not as hard as it sounds. You're going to see, we're going to go through these examples. Okay, so let me pull up. We're going to go through 2 examples. You can write these ones down. Okay, and you're going to see that the steps that we go through are almost identical to the acidic steps. First thing we're going to do is assign oxidation states to everything. Okay, so okay. We'll start off with the oxidation half reaction. We're just going to put a 2 up here in front of the iodine so that we have the same number of iodines on both sides. Okay, then we have a charge of -2 on our reactant side and a charge of 0 on our product side. So we're going to add 2 electrons over here so that our charges are the same. Okay, and then again, we're done with that one for now. So we come over here, our manganese atom number is the same. I have 4 oxygens here and I have 2 oxygens here. So I'm going to add 2 more waters. So I have a total of 4 oxygens here. Now I have 4 hydrogens here and I have no hydrogens here. So I'm going to add 4 hydrogen ions. And this is the point where we're going to say to ourselves, well, you can't have hydrogen ions in a basic solution. So to take care of that, I'm going to neutralize these 4 hydrogens by adding hydroxide ions to both sides. Okay. My 4 hydrogens plus my 4 hydroxide ions are going to create 4 waters. And then over here, I'm going to have MnO2 plus 2H2O plus 4OH minus. Okay. Now, what we discussed before comes into effect here regarding the same species on opposite sides of our reaction arrows. If I have 4 waters here and I have 2 waters here, 2 of these waters, these 2 are going to cancel out. 2 of these are going to cancel out. Okay, so what I'm actually left with is going to be 2 waters plus MnO4 minus gives me MnO2 and 4 hydroxides. Okay, and now I have to balance my electrons. I go right back into the normal balancing here. I have 4 hydroxides on the product side. That's a total of -4. I have a neutral, 2 neutral waters, and a permanganate ion that has a -1 charge. So I'm going to have to add 3 electrons to this side for my charges to be the same. Right? Because if I have 3 electrons with -1 charges and one of these, now my total charge on that side is -4, and I'm matched up. Okay, but I have to make this number of electrons equal. So I'm going to multiply this half reaction by 3, and I'm going to multiply this half reaction by 2, right? Because 6 is going to be my common number when 1 is 2 and 1 is 3. And I'm going to rewrite those half reactions under here so I can add them together. Okay, so I end up with 3 times 2 is 6 iodines, iodide ions rather. 3 iodines and 6 electrons. And for my reduction half reaction, I'm going to end up with 6 electrons plus 4 waters plus 2 permanganate ions gives me 2 2 plus 8 OH minus. Okay. And now I'm just going to add these together like I did before. 6 electrons on the product side, 6 electrons on the reactant side, those cancel out. I have nothing else in this reaction that cancels out, so everything else is going to come down now into my overall reaction. And that's going to be 6 I minus aqueous plus 4 H2O liquid plus 2 MnO4 minus aqueous yields 3 I2 aqueous plus 2 NO2 solid plus 8 OH minus aqueous. I know I drop the states of these things when I'm going through the balancing process. That's just because I run out of room, but it's always a good idea when you're writing your overall reaction to make sure that you put all the proper states back in. Okay. All right, so we're going to look at the next one, final example. And this is a good one where, you know, if you've just been watching me do this, maybe take a minute here and actually try to do this one on your own, okay, before you watch me do it. All right, so take a second, write that down, maybe pause the video and try to do this one on your own. All right, so starting with step 1. Okay. So now we're going to trace this. Our chloride or chlorine is going from +1 to -1. That's going to be reduction. Our chromium is going from +3 to +6. That's oxidation. Okay, so step by step now. We have 1 chromium, that's fine. I have 4 oxygens here and 4 oxygens here, so I don't have to add water anywhere. I have 4 hydrogens here and none here, so I'm going to add 4 hydrogens here. Okay, now to get rid of these hydrogens, because I'm in a basic solution, I'm adding 4 hydroxides to each side. My 4 hydrogens plus my 4 hydroxides are going to combine and form 4 waters. Okay, and my 4 hydroxides that I added over here are just going to stay over here. Okay, now we can look at the charges. We got a -2 charge here. I've got -4 from my 4 hydroxides and a -1 here. It's a total of -5. So I'm going to have to add 3 electrons here to get my charges to match. Okay, so now I have a -2 plus a -3 is going to be a -5, and I have a -5 here. Perfect. My reduction half reaction, my chlorines are balanced. I'm going to add 1 water over here so that my oxygens are balanced. Now I have 2 hydrogens here, so I'm going to add 2 H pluses over here to balance out my hydrogens. Can't have hydrogens in a basic solution, hydrogen ions in a basic solution, so I'm going to add 2 hydroxides to each side. The hydrogen plus the 2 hydrogen ions plus the 2 hydroxide ions are going to combine to form 2 waters. So I'm just going to rewrite this side of the reaction as 2H2O plus ClO minus. And these 2 hydroxide ions are just going to stay right here. If I have 2 waters on the reactant side and 1 water on the product side, this product water cancels out, and 1 of my reactant waters cancel out. So this is actually going to be H2O, just one of them, plus ClO minus yields Cl minus and 2 hydroxide ions. Okay, now I'm going to look at the charges. -1 plus 2 -1s, that's going to be a total of -3. Over here, I have a total charge of -1, so I'm going to need to add 2 electrons to the side so that my total electron, or my total charge value here is -3 on both sides. Okay, now I'm going to add these together. See, this is already a more interesting looking reaction. I have a lot of stuff that I'm going to get to add together now. So my reaction that has 3 electrons, I'm going to multiply by 2. My reaction that has 2 electrons, I'm going to multiply by 3. I'm going to rewrite both of them under here so I can add them together. Okay, so 2 times 4 is going to be 8 hydroxides plus 2 of these. Yields 2 of these plus 8 plus 6. Okay. And now I'm going to do the same thing for my reduction half reaction. This is going to give me 3 of those, 3 of those, 6 electrons, 3, and 6. Okay. So this one's definitely more interesting. We can track down similarities on opposite sides of the reaction here in more than one place. Usually, the last few examples we've seen, our similarities were only in terms of the numbers of electrons on both sides of the half reaction. In this case, we also have waters, and we also have hydroxide ions on both sides. So we're going to have to take care of all of that. Okay, our electron numbers are exactly the same, so they're going to fully cancel out. We have 8 hydroxides here and 6 here. So all 6 of these are going to cancel out. And we're going to have 2 of these left over. So you see how that works? 8 minus 6 is 2. We have 8 waters here and we have 3 waters here. So all 3 of these waters will fully cancel out. We'll have 5 waters left over on the product side. Okay, that's everything. So whatever is left over is going to come down into our overall reaction. So that is going to be 2 hydroxide ions, 2 CrOH4 minus, 3 ClO minus, 2 CrO42 minus, 3 Cl minus, and 5 H2Os. Okay, and that's the overall balance reaction. Not hard to do at all. It's not even that time consuming once you get the hang of it, because we're writing out every step like very clearly here, and you do need to write out your steps. But there's certainly some ways that you can shorthand some of this so that you don't have to rewrite every single thing. I want to make sure that's very clear for you. And until you get very comfortable with it, don't see it as like a sign of weakness if you have to keep rewriting every step. That's how you're going to remember it. Okay. But it's important that you know how to do the redox reactions, because that is going to come into play for the rest of the reactions that we have to do. All right. So let's look at the next kind of question, and this is where we're going to see this oxidation and reduction kind of in practice. Okay. Here we're given a balanced reaction. Okay, they're telling us that it's balanced in this case, so we don't have to balance it ourselves. And we have to use our reduction potential table from our textbook to figure out what the standard cell potential is for the following reaction. Okay, so let's write down the reaction. Pause for a second while I... Okay, so this is our overall reaction. And the first step here, when you're trying to answer this question, which again, we're calculating the standard cell potential. Before we can do this, we have to figure out what is being oxidized and what is being reduced. Okay, so step one is going to be to, I guess, assign oxidation and reduction. In this case, it's pretty easy to see because our solid aluminum is forming aluminum 3+. So we know that if it's going from an oxidation of 0 to +3, that has to be oxidation, meaning that the rest of this is going to be the reduction half reaction. Okay, but if it's not clear right from the balanced equation that you're given, or the equation that you balance for yourself, you should be able to assign oxidation states to everything in the reaction, and you'd be able to figure out that the aluminum is being oxidized and the nitrogen is being reduced. All right, this is an important step because step two is going to be to figure out which one is your anode and which one is your cathode. Okay, so we'll call step two assign anode and cathode. Oxidation is going to occur at your anode. Reduction is going to occur at your cathode. Okay. Now we have in that table that we were given, we have the reduction potential values. Let's bring up that table again. Give you guys a chance to see it. And what I recommend doing is writing down the reduction potentials of each of these reactions exactly as they're written in the table. Okay, without changing signs or anything like that. Just write down the values that are given in the table for now. Okay, so our aluminum reaction is going to have an E value of negative 1.66 volts. And our nitrogen reduction reaction is going to have, where's that at? 0.96. I don't know why I couldn't see that. It's right on my screen. Okay. Now, your textbook gives you an equation that you can use and not have to change the signs of your E cells from the reduction potential table. Okay. I know that the equation that you're given in Professor Sheehan's notes is a little different than the equation in your textbook. That equation involves you understanding which is oxidation and reduction, which is not hard, and flipping the sign and before you're adding them together. Okay. What the reaction that we're going to work with here that your textbook works with looks like this. E cell equals the E value for the cathode minus the E value of the anode. This equation incorporates the sign flip that you need to do, which allows you to just plug the values directly into this equation, or I should say vice versa in this case. Okay, no, if you're using the equation from your textbook, do not flip any signs. If you're using the equation that Professor Sheehan gave you in the notes, that's when you need to flip the signs. Okay, so to find your E cell here, you're going to do the E value for your cathode, which is this, 0.96 volts. And I recommend also keeping both of these values in parentheses so that you don't confuse yourself with any sign situations that happen. Sometimes you end up dropping a sign over here if you don't, okay? So now we're subtracting the E value for our anode, and that's going to be the negative 1.66. Okay, negative minus a negative, it's going to be a positive. So we're going to end up with an E cell here of positive 2.62 volts. Okay, so pretty easy to do, especially once you have a good understanding of how to look at redox reactions. Okay, this is going to be the next one that we try. Again, try this one on your own before you watch me do it. So that's going to be the best way to be good at it. Okay, so this is the reaction we're going to look at now. Again, we can figure out where oxidation and reduction is happening pretty easily by looking at the balanced equation. We have a +2 oxidation on the lead here and a 0 here. That's going to be reduction. So this is going to be our cathode. The chromium goes from a 0 to a +3. Okay. So that's going to be oxidation at your anode. Okay, I always remember it because O and A are vowels, so it's like they go together. And R and C are both consonants, so they go together. I don't know if that's helpful. That's just how I remembered it when I was learning it. And now we want to find the reduction potential values for these reactions, and you have to be very aware of the half reactions that you're looking at. If we look back to the table, okay, the lead one is pretty straightforward because we have the lead 2+ ion plus 2 electrons gives us solid lead. So we can write down that reduction potential value. So the E for our cathode is going to be negative 0.13 volts. But for the chromium reaction, there are multiple chromium ions on the table, and you have to make sure that you write down the reaction where the chromium 3+ and the 3 electrons is forming the chromium solid, because our reaction had chromium solid on the reactant side, not the chromium 2+ ion. So we have to make sure that we're looking at the right reaction here. So the E value for our anode is going to be negative 0.73 volts. What you're also going to see in general when you're looking to decide, which is my anode and which is my cathode, your anode is going to have the more negative E value. And your cathode is going to have the more positive value. So if you're just looking up the half reactions, or if you're given the half reactions and you need to make a determination which is the anode and which is the cathode in your electrochemical cell, this is how you do it. The more positive E value is going to be your cathode. And now it's just going to be a matter of plugging this into the equation that we're using, right? So E cell equals E cathode minus E anode. So we're going to have negative 0.13 volts minus negative 0.73 volts. And that's going to be an E cell of positive 0.60 volts. Okay. The next question that we're going to look at is a little more involved. This says, without calculating E cell, predict whether each of the redox reactions is spontaneous. If it's spontaneous as written, then we're going to sketch the electrochemical cell. Okay, and these are, very basic sketches so you can see what's happening. If the reaction is not spontaneous as written, then write an equation for the spontaneous direction and then sketch that cell. Okay, and in our sketches, we're going to include the anode, the cathode, and the direction of electron flow. All of that sounds more complicated than it actually is, I promise. Okay, so after we write out our reaction, again, this doesn't want us to necessarily calculate E cell to figure out whether the reaction is going to be spontaneous or not, but we can use the reduction potential values to help us figure this out anyway. Okay, so we're going to look at the reaction that we're given here, and we see that we have iron is going to be oxidized in this reaction. And we see that Mg goes from +2 to 0, right? So magnesium is going to be reduced, or I guess we could say Mg2+ is reduced. Now we just want to look at the reduction potential values associated with each of these reactions, because remember what I told you, that the numerical value that's associated with that reduction potential is going to tell you whether you're going to find that reaction at the anode or the cathode. Okay, so the reduction potential for your iron is going to be negative 0.45 volts. The reduction potential for your magnesium is going to be negative 2.37 volts. Okay, and what did we just write down in that last slide? The anode is going to be more negative. So the anode should be more negative. And the cathode should be more positive. Okay, but in the reaction that we were given, the way that this is written and presented to us, it's saying that the iron is oxidized, and the species that's oxidized is the species that goes at the anode. Magnesium is being reduced, so it should be at the cathode. All right, but these reduction potential values would not allow that reaction to occur naturally because of the values of each one. Okay, the spontaneous version of the reaction is going to be the version where your magnesium is at your anode and your iron is at your cathode. So we can rewrite the equation in the reverse direction to make this happen. If we write Mg solid plus Fe2 plus yields Fe solid plus Mg2 plus Well, now your magnesium is being oxidized. And your iron is being reduced. And this makes sense with the E values for each one, because the magnesium wants to be at the anode. It wants to be oxidized. Okay, and then your iron obviously wants to be at the cathode and it wants to be reduced. Okay, once you have the direction of the reaction correct, then you can draw yourself a little sketch of a cell. They don't have to be very fancy, like 2 rectangles here. You can have your salt bridge. You just have to kind of label it salt bridge. And this would be the kind of connecting wire. Your electron flow is going to be from anode to the cathode. Your anode goes on the left. Your cathode goes on the right. At your anode is going to be your magnesium solid converting to magnesium ion, magnesium ions. I don't know why I had such a hard time saying that. So let me actually cut this a little bit and put it in like this so that I can draw a solid piece of metal there. And your wire would attach to the metal, and then your wire would attach to the metal. Okay, so that metal on your anode side is going to be magnesium solid. In your solution here is going to be your magnesium ion. Okay, then in the solution here is going to be your iron ions, Fe2 plus. And then your solid here is going to be Fe, solid. Okay, you might be asked to write the cell notation of something like this, which is basically a representation of your electrochemical cell in shorthand form. And that's just going to be you reading the electrochemical cell from left to right. Okay, so it starts with your magnesium solid. And then there's going to be a line, and you're going to write the next component. Your magnesium solid is going to end up converting to magnesium ions. You can keep the states in there. Then you're going to encounter the salt bridge, which is a double line. And then you're going to encounter the iron ions. And then you're going to encounter the iron solid. Okay, so this is called cell notation. All right, let's look at the next example. In this one, we're working with iron and lead instead. Okay, so we're going to erase this. And we're going to see that iron in this case is going to be reacting with lead, so it's going to behave differently because lead has a different reduction potential. Okay, when iron and magnesium were paired up, magnesium wanted to be oxidized. But when iron and lead pairs up, iron wants to be oxidized. And that has to do with those reduction potential values associated with each one. So in this case, we're looking at solid iron plus aqueous lead ions produces iron ions and solid lead. Okay, so we see that this is going to be oxidation. This is going to be a reduction. And if we look up the reduction potential value of iron, it's going to be negative 0.45 volts. The reduction potential for lead is negative 0.13 volts. So this makes sense. This is more negative. That should be the anode, in this case, and we see from the reaction that it is. The more positive value should be the cathode, and we see from the reaction that it is. So the reaction is going to be spontaneous the way that it's written now. Okay. And we can draw an electrochemical cell based on the reaction as written. So we'll make our little rectangles, make our salt bridge, make my metal pieces and a little wire connecting them. Make our solution. Okay, so there's our salt bridge. That's going to be the anode, that's going to be the cathode. Our electrons are going to flow. Electrons are going to flow in this direction from the anode to the cathode. And the solid in our anode is going to be the Fe. And in the solution is going to be Fe2 plus. In the solution at our cathode is going to be Pb2 plus. And our solid is going to be Pb solid. Okay. And then we can write out the cell notation for this as well. That's going to be Fe solid, and then a line, Fe2 plus aqueous, and then our salt bridge double line, Pb2 plus aqueous line, Pb solid. Okay. And we could actually calculate the standard cell potential. I don't know, just blanked on that completely for this and kind of prove that it's spontaneous anyway. All right, we can calculate that E cell because we have the values. The question didn't ask us to do this, but we kind of just do it anyway to kind of prove it to ourselves. So again, it's going to be E cathode minus anode. So it's going to be negative 0.13 volts minus negative 0.45 volts. And we get positive 0.32 volts. See? And we wouldn't get that value if it was not spontaneous. All right. Next question asks us to use the tabulated, let me put it up there for you. This question says to use the tabulated electrode potentials to calculate delta G for the following reaction. Okay, so this is just going to be building on the examples that we've already done. We're going to calculate E cell, okay? And we're going to look at the overall reactions for each one of these. And we have to figure out how many electrons were used in the reaction, okay? Because that's gonna help us relate these two values. Once we have our E cell value and our number of electrons, then we're going to be able to calculate delta G. Okay, let me take a second and write out this reaction real quick. Okay, so once I have the reaction written out here, first thing I want to do is figure out which reaction is my oxidation half reaction and which is my reduction. Okay, and I want to know how many electrons were used in this reaction. Okay, so I see that I have an oxidation of 0 to -1 here. So I know that that's going to be a reduction. And I have -1 to 0 for my bromine. That's going to be oxidation. All right. So I'm going to just write these out so I can visualize how many electrons that I've used. It might be that you can look at it and you can see it right away, but I'd recommend that until you are very good at this, you just take the extra time to write out both half reactions. Okay, so you have I2 solid plus 2I minus. So I have a -2 charge here and a 0 charge here. That means that I had 2 electrons over here. Okay. This I already said, I'm going from 0 to -1. This is going to be my reduction half reaction. Or I can write that right in as my cathode half reaction. Okay, and I can find this reduction potential value in my table. Okay, so all these questions where they're asking you to calculate E cell, you have to do that from the reduction potential table in your textbook. Okay, you're not just going to know these values off the top of your head. So the value for this half reaction is going to be 0.54. Okay. My second half reaction is going to be the 2Br minus. Sorry, I was like, what is wrong up here? So I didn't put an arrow there. It's going to be the 2Br minus, gives me Br2. Okay, this is a -2 charge. This is no charge, so I'm going to have 2 electrons here. And the reason I did this is because I wanted to know what the electron value was that cancels out when I add these two reactions together. Okay, so I'm going to star this and say I canceled out 2 moles of electrons. Okay, this reaction here where I'm losing electrons is going to be my oxidation half reaction, which will be at the anode. And the E value for this is going to be positive 1.09 volts. Okay. So like right off the bat, I can already see that there's a spontaneity issue with this, but we're going to prove it using the delta G. Okay. So I'm going to find E cell from these two values. So it's going to be E cathode minus E anode. So it's going to be 0.54 volts minus 1.09 volts. So my E cell is going to be negative 0.55 volts. All right, negative E cell, no good for spontaneity. But on we go, we're going to keep solving it out. The equation that we're going to use to relate our E cell to delta G is this one. Delta G equals negative N times F times E cell. Right? So what we were doing with our work so far is we were finding our N value and we were finding our E cell value. Okay? Your F value is Faraday's constant. Okay, and this is going to be 96,485 coulombs per mole of electron. Okay. So now we can figure out what our E cell is. Oh, and if this was not clear, the N value that we're using here, the N is going to be the number of moles of electrons canceled out. Okay, so in this case, our N value is going to equal 2 because we canceled out 2 moles of electrons. So delta G is going to equal -2 I'm going to put it over 1 since Faraday's constant, it ends up being a fraction, times 96,485 coulombs over 1 mole of electrons, and then times E cell, which is going to be negative 0.55 volts over 1. Okay. So we end up, I guess we need to do this to like 2 sig figs. So delta G for this reaction is going to be positive 1.1 times 10 to the 5 joules. I forgot to go over that part before. Because when you end up with a volt, the unit of a volt, so over here we have negative 0.55 volts. The unit of a volt is equal to, let me write it up here before we get there. 1 volt equals 1 joule over coulomb. Okay, so when you do your E cell calculation here and you get negative 0.55 volts, you can rewrite that as negative 0.55 joules per coulomb, which is what I should have written it as here, so it was less confusing. And that's how you're able to, use that unit of volts in this calculation. So now you see how everything is going to cancel out, like our coulombs cancel out and we're just left with joules. But we end up with a positive delta G value, and we know that a positive delta G value from the last chapter means that we do not have a spontaneous reaction. Okay. All right. Next example. Share the screen. You guys should try to do this one on your own. Okay, so let's start by separating these into our half reactions so we can add them together. We have Na solid going to Na plus, so that's going to be a 0 to a +1. That's going to be oxidation. So we have 2 Na. Okay, so for this half reaction to hold up, that means that we had 2 electrons that we were working with here, right? Because we had a positive 2 charge from the 2 sodium ions, so we need 2 electrons here. And if we look up the E value for sodium in our table, we see that it's negative 2.71. We already said that this is going to be oxidation, so this is going to be our anode. Okay, for our reduction half reaction, we're going to look at the rest of that. That's going to be 2H2O. Gives us H2, 2OH minus. This is going to have a negative 2 charge because we have 2 hydroxide ions. Everything else is neutral, so that means that we had 2 electrons over here. Okay, so again, we focused in on that electron value. That means that the N value here is going to be 2. That's the number of electrons that were canceled out here. The E value for this half reaction, if we look it up in our table, is going to be negative 0.83. Okay, so now we're going to calculate our E cell. So we're going to have, oh, I should write cathode after that one. So we have negative 0.83 volts minus negative 2.71 volts. It's going to be 1.88 volts. It's already looking better than last time. And 1.88 volts is going to be 1.88 joules per coulomb. Okay, so now we can plug it into our delta G equals NF E cell. Negative NF E cell. So negative 2 moles of electrons times Faraday's constant, 96,485 coulombs per mole of electron. Times our E cell, which is going to be 1.88 joules per coulomb. And we end up with negative 3.63 times 10 to the 5 joules. Negative delta G value indicates a spontaneous reaction. All right. Now we're going to look at how our cell potential relates to our equilibrium constant. So that should be exciting for everybody. Let's look up there. Like, yay, get our K values again. They'll never go away. It's true, they really won't. We just keep seeing it. Okay, so this question asks us to find K given an overall reaction. And you're going to see that this is very similar to the process that we did before. We're just going to be finding K instead of G. And our equation is just a little bit different, okay? For this one, the equivalency is that E cell equals 0.0592 volts over N log K. Okay, so you see that if we find E cell and if we find N, we're again going to be able to calculate K. So we're going to start the same way we did last time by splitting these up into their half reactions. So we can look at their E cell values and also figure out the moles of electrons that were used in the reaction. So we have Cu copper to our copper ion. So we see here that we would need 2 electrons for our charges to balance out. Here I have 2 hydrogen ions producing hydrogen gas. So I need 2 electrons on this side for the charges to cancel out. Sorry, my voice got all weird. My allergies are just killing me today. So this is our N value. Okay, now we're going to look up the reduction potential tables. We see that our copper is being oxidized, so it's going to be the anode. Okay, and the reduction potential value for the copper is positive 34 volts. Oh, positive 0.34 volts, sorry. And the reduction is happening with the hydrogen, so that's going to be at the cathode. And that's going to be an E value of 0.00 volts. So now to find E cell, it's going to be the cathode minus the anode. So we see that our E cell is going to be negative 0.34 volts. So the fact that our E cell is negative means that the reaction's not going to be spontaneous. We're going to be expecting a very, very small K value when we calculate this. All right. So we have our N value, we have our E cell value. Now we can work with this reaction here. So negative 0.34 volts equals 0.0592 volts over 2 log K. So now I'm going to multiply both sides by 2 over 0.0592 so that I can cancel this out from this side and move it over here. So 0.34 negative times 2 divided by 0.0592 is going to be negative 11.486. Okay. Now to isolate K, I'm going to have to raise both sides 10 by 10 to the 10 to the 10. That's how you say it. So I'm just going to do that and that. This is going to cancel out. And I get a value of 3.26. I think that I'm going to have to do 2 sig figs here. So 3.3 times 10 to the negative 12 is going to be my K value here. And it's very small like I expected because this E cell value is negative, right? So that a negative E cell value doesn't indicate a reaction that's going to proceed very strongly in the forward direction, and a small K value reflects that. All right. Let's look at the second reaction. Again, try to do this one on your own. Okay, so let's start off by dividing this up into our half reactions. We have the iron solid going to the iron ion, so that's going to be our oxidation. Okay, so if we're looking at this in terms of electrons, we have a 0 charge here, and we have 2 times positive 3, which is a positive 6 charge here. So we're going to need 6 electrons to equal out the charges. Okay, for our other half reaction, we have, oops, let me write that a little further over so it matches. We have 6 hydrogen ions, gives us 3 hydrogen gases. So that's a positive 6 charge, that's a 0 charge. So we're going to need 6 electrons here. So now that we found the number of electrons that cancels out, we found our N value. Okay, we've already said that this is going to be oxidation and this is going to be a reduction. So this is going to be our anode and this is going to be our cathode. So now we're just going to look up the reduction potential values for each one. For iron, the reduction potential value is going to be negative 0.036 volts. For the hydrogen, it's going to be 0, again, 0.00 volts. Okay, now we can find E cell. All right, now we can do our K calculation. We have everything we need. So we write out our equation. Another thing you can do when you're going to solve this, you can just rearrange this equation before you even start so that you're solving it for the log of K instead, right? So you could say that based on this reaction, that the log of K equals E cell times N over 0.0592 volts. Like these are equivalent equations, right? And I don't know, maybe it'll be easier because you're solving for K to have all of the other stuff that you're going to fill in on the other side before you start actually putting real numbers in. Totally up to you. But if we do it like this, you see that log K is going to be 0.063 volts times 6 over 0.0592 volts. So that'll cancel out. And we're going to get 3.649. Just make a little box around there. Okay, so we're going to raise both sides to the 10. And K in this case is going to be equal to 4.5 times 10 to the positive 3. Okay, that's a large number, so we would expect that because we have a spontaneous reaction, right? It's not like the biggest K value we've ever seen, but this is also this is also not the most positive E cell that we've seen. So, there's kind of a correlation between the values that you're seeing here. But at least we see that we have a positive exponent in this case when we have a spontaneous or a positive E cell. All right, so the next questions we're going to look at are to figure out the cell potential for electrochemical cells when we have non-standard conditions. So let me put up the questions so you could take a look at them before we start talking about it. Okay, so when you first see a question like this, it might look very confusing because there's a lot of different notations in here. But I want you to focus on the similarity to the equations that we've seen before, okay? Specifically when we were looking at like the delta G of a reaction when it was at non-standard conditions, we used the Q value again, our reaction quotient, again, to figure out what our delta G value was. And we're going to do the same type of thing here. I'm just going to write the equation over here for us to look at briefly. I'm going to use the rest. I'm going to have to use the rest of the board for to solve the problem. But just before we start solving the problem, the reaction that we're going to try to end up getting to is this one, that the E cell, and this is the value that we're trying to solve for here, is going to be equal to the standard E cell minus 0.0592 V divided by N log Q. Okay, so we're going to need to figure out a few things before we can solve for the equation that we need to solve for. We need to be able to calculate the E cell value and the N value, which is fine because we've been doing that for the last few problems and it's going to be the same process. We also need to calculate Q before we can solve this equation, okay? We can't calculate Q, however, until we know what the full balanced redox reaction is between these two half reactions, okay? So the first thing we're going to do is balance the reactions and figure out our N. From there, we'll have a reaction that we can use to figure out Q. Okay, and we'll also be able to figure out E cell once we do that. So let's get into it. Okay, I'm going to focus in right away on the fact that I have 2 electrons in my oxidation half reaction and I have 3 electrons in my reduction half reaction. This number of electrons has to be the same. Okay, that means that I'm going to have to multiply my oxidation by 3, so I have 6 electrons. I'm going to have to multiply my reduction half reaction by 2, so I have 6 electrons. All right, so I'm going to rewrite both of those underneath because I'm going to end up adding them together like earlier when we were balancing redox. I'll leave out the concentrations for now because we'll get back into those when we're calculating Q. Now I'll write the reduction underneath it. Okay, and now I'm going to add these together and cancel out what needs to be canceled out. And I need to add everything else up into a full balanced reaction because I need that full balanced reaction to find Q. All right, so I know that my electrons are canceling out. So I know that my N value equals 6. Just note it at the bottom of the board here. We'll pull that up later. See, I just tucked it over here for us to look at in a minute. So we have 2 MnO4 minus plus 3 copper solids plus 8 H plus 3 Cu2 plus 2 MnO2 solids and 4 H2O liquids. Okay, now what I'm going to do is underneath each of the components that had a concentration in the problem, I'm going to write that concentration just so I have it very clearly laid out for me. So my permanganate ion had a concentration of 2 molar. My copper is a solid, so it's not going to be included in my Q calculation. my hydrogen ion is going to have a concentration of 1.0 molar. My copper ion is 0.010 molar. My MnO2 is a solid, H2O is a liquid, so those aren't part of our Q calculation. All right, so finding Q, it's going to be products over the reactants raised to their coefficients, and we're not including solids and liquids in this. So it's going to be the concentration of Cu2 plus to the third divided by the concentration of MnO4 minus to the second times H plus to the eighth. So we end up with 0.010 cubed over 2 squared over 1 to the 8. Calculate that. So we get 2.5 times 10 to the negative 7. Okay, so now we have two things that we need. We have a Q value and we have an N value. Now we need an E cell value. Okay, so we're going to go back and look at our standard reduction potential table. The reduction potential for copper is going to be positive 0.34 volts. The reduction potential for the permanganate is going to be positive 1.68 volts. Okay, so again, this is going to be our anode, and this is going to be our cathode. All right, so to calculate E cell, we're going to use those values. So E cathode is going to be 1.68 volts minus our anode, which is going to be 0.34 volts. It's going to equal 1.68 minus 0.34, which equals 1.34 volts. So this is going to be our E cell value. Okay, let's push that up here so we can see these are all the values that we're going to need to solve for our E cell at this particular set of conditions. Okay, so now we're going to look back at that equation. E cell is going to be equal to E cell standard minus, and the minus, what the terms there stand for is the change in the conditions that we've made from our standard set. That's what this whole section is going to account for. So it's 0.0592 V over N log Q. So we have 1.34 volts minus 0.0592 V over 6 log 2.5 times 10 to the negative 7. So let's see what that term comes out to be. Okay, so that ends up being negative 0.06514. So our E cell value at this set of conditions is going to be positive 1.41 volts. Okay, so it's a few steps, but it's not too bad. All makes enough sense, I think. All right, so let's try the next one. All right. So for our oxidation, which we can write, we can write that in as our anode right away anyway. That's going to be the nickel solid goes to nickel 2 plus 2 electrons. And the reduction, which is going to be our cathode, is VO2 plus 1 plus 2H plus 1 electron, O2 plus H2O. Okay, and in this case, I'm going to just write the concentrations of the different aqueous components after I balance out the reaction after I balance out this reaction and figure out what my overall reaction is, because it just gets too mushed together otherwise. So I see that I have 2 electrons here and I have 1 electron here, so I'm going to multiply this reaction by 2. Okay, that's going to give me the electron values I need to cancel it out. I'm just going to rewrite this a little bit so I can use the space up here. This is going to be nickel solid. Okay, and I'm going to multiply this whole reaction by 2 and just rewrite it with its new values. So we're going to have 2 VO2 plus 4H plus 2 electrons, 2 of these, and 2 of these. Okay, and now I can add these together. My electrons are going to cancel out. So my N value is going to be 2. And I end up with 2 VO2 plus aqueous plus 4 H plus aqueous plus nickel solid produces nickel ion aqueous plus 2 O2 plus aqueous plus 2 H2O liquid. Okay, and now I can go back to the problem itself and I can just write the aqueous concentrations under everything that's aqueous. So my nickel concentration is going to be 2.0 molar. My solid nickel obviously isn't going to take part in my Q calculation. My VO2 plus is going to be 0.010 molar. My H plus is going to be 1 molar. My O2 plus is going to be 2 molar. And my liquid water is not going to count in my Q calculation either. Okay, so for my Q, it's going to be the concentration of Ni2 plus, not raised to any coefficient, times the concentration of O2 plus squared over the concentration of VO2 plus squared times the concentration of H plus to the 4th. Okay, so we get 2 times 2 squared over 0.01 times 0.01 squared times 1 to the 4th. Okay, go back and fix your sig figs when you're done with this. I'm just running out of room here. So 2 squared times 2 equals. Okay, so we end up with a Q value of 8.0 times 10 to the positive 4. All right, so we have 2 of the values that we need so far. Okay, so now we're going to look back at our standard reduction potential table, and we're going to find the E for our anode, which is our nickel. You find that in the table, and it's negative 0.23 volts. The E for our cathode is going to be the reduction potential for this mess down here. And you can find that reaction in the table, and that's going to be positive 1.00 volts. So to find our E cell, E cathode minus E anode, 1.00 volts minus negative 0.23 volts. So we're going to end up with an E cell of positive 1.23 volts. And that is the last value that we need. Now we can calculate our E cell at this set of conditions. .0592 volts over N log Q. Okay, so we have 1.23 volts minus 0.0592 over 2 log of 8.0 times 10 to the 4. So our new E cell value is going to be positive 1.08 volts. All right, now we're going to look at something a little bit different. We're going to look at a couple of electrolysis reactions. In this case, they're giving us one mixture of molten aluminum bromide and magnesium bromide. And we need to figure out the half reaction that's occurring at the anode and the half reaction that's occurring at the cathode for the electrolysis that's happening here. Okay, so take a second to write down that info. Okay, so before we actually look at this problem, I just want to say a few things about electrolysis and electrolytic cells in general, because the process differs a little bit from the Voltaic cells, which are the ones that we were working with earlier. Okay. When we see electrolysis occurring, we're looking at a cell where we have some kind of electrical current. Okay. It's going to drive a reaction that would be non-spontaneous normally forward. Okay. So a lot of the things that we've learned already about the cells are kind of opposite for electrolytic cells. The purpose, there's quite a few purposes for electrolysis, but one that we're going to look at in the, not in the example we're working on now, but in the next one, is the idea of plating out metals. And that's where we can actually cause metal ions to form solids on another metal surface. So then we can actually collect that metal. Okay. So this is a definition of electrolysis. Now, what that means for our cells themselves, the cells that we're looking at, looks a little bit like this. So in all of our electrochemical cells, two things are true, okay? So in all electrochemical cells, oxidation is at the anode and reduction is at the cathode. Okay, that's not going to change. Okay, what does change is the species that's at the anode or the cathode. Okay. So in a Voltaic cell, which are the ones that we were looking at before, our anode is going to be its own source of electrons. Okay. So the anode is going to have a negative charge. All right, and the cathode has a positive charge, and it's going to pull the electrons. The opposite is true in an electrolytic cell. In an electrolytic cell, our anode is going to have a positive charge. Okay, and that's why we're going to need some kind of current to drive the reaction. The electrons are actually going to be forced into the cathode, right? And that cathode is going to have a negative charge. All right, so these are the differences between a voltaic cell, which are the ones we were looking at before, and an electrolytic cell, which we're going to be looking at now. Because we're going to have to do a little bit of reasoning to answer this question. That's why we have to go over this stuff. So we're going to be looking at this mixture. All right, and we're going to look and we're going to see how the different components would break up. Okay. So if we have aluminum bromide and magnesium bromide, we'd end up with 3 different ions, right? We'd have our Al3 plus, and we would have Br minus, and we would have some Mg2 plus and Br minus. Okay, so we know that there's only one source here of the well, there's only one anion here, and that's going to be the bromide anion. Okay, and we have 2 potential cations. Okay. In your electrolytic cells, the anion is going to be oxidized and the cation is going to be reduced. So let's write that down. It's reduced. There's only one anion type, so that's fine. We know what our oxidation reaction is going to be then. It's going to be Br minus plus 1 electron, or sorry, we're oxidizing this one. So it's going to be Br minus goes to Br 2 gas. For this to work out, we're going to need 2 of those, 2 bromines, and we have a -2 and a 0 charge. So we're going to need 2 electrons. Okay. And again, normally you would see in a voltaic cell, you know, the anion and the cation situation would be reversed. Okay, but because we're at an electrolytic cell, that's why our bromide ion is going to be oxidized. All right. Now we have to figure out which cation is going to be the cation that is going to be reduced here. And we're going to look at the reduction potential values for this. So we're going to write out the 2 reduction reactions here, the one for aluminum and one for magnesium, and we're going to compare them. So we have Al3+, and for this to be reduced, it's going to have to gain 3 electrons to form aluminum solid. The magnesium is going to have to gain 2 electrons to become magnesium solid. And if we look up the reduction potential values on our table, the one for aluminum is -1.66 volts. And magnesium's is -2.37 volts. Okay. And like we said early, like right at the beginning of this whole recording, the more positive of these 2 values is the more likely to be reduced. So this is the reduction reaction that's going to occur. Okay. Magnesium is that the reduction is too negative for it to occur. The aluminum is going to occur first, right? So this is what's going to be going on at your cathode. All right. So that's what this question is asking us to do, figure out which half reaction is going to be occurring at the anode and which is going to be occurring at the cathode. The bromide is being oxidized, so that's going to be occurring at the anode. And then our cathode is going to favor this particular half reaction because it has a more positive E cell value or reduction potential value. All right. I know this is a weirder concept so just try to follow along with it. The second question was an aqueous solution of lithium iodide. Aqueous LiI. All right, so we have to see what's happening here. We have a lithium ion, we have an iodide ion, and we have water, right? So it's aqueous. So we're going to look at all of the potential reactions that are happening here. Okay. We have I minus is going to go to I2, right? So that means we need 2 iodines, and we'll need 2 electrons here. Our lithium is going to be Li plus 1 electron, gives me Li solid. Okay, and then we're going to have to look at the water. Okay, so for when we're oxidizing the water, that means we know that the anion is going to be oxidized, right? I should have written that out a little more clear. The oxidation is our anion. Okay. In this case, we have to compare the oxidation of the anion to the oxidation of the water and see which one is more likely to be oxidized. And then we have to do the same thing for the lithium down here. So reduction is going to be the cation. And in both of these cases, it's going to be or water, because there's nothing else competing here except for the lithium iodide and the water. Okay, so we're going to look at the H2O. And you go back to your what am I trying to say? Your standard reduction potential table to kind of help you out with this, because you're going to be able to pick out the different water reactions. You're looking for a reaction in this case where water is going to be losing electrons. In this case, you're looking for a reaction where water is gaining electrons. Okay, so if we look back at our reduction potential table, we see that the reaction where water is losing electrons is this one. O2 gas plus 4H plus 4 electrons. Okay, and the E value for this reaction is going to be 0.82 volts. The E reaction for the iodide is going to be 0.54 volts. Okay, so for the oxidation portion of it, that's occurring at the anode, we're looking for the more negative value. That's what's going to occur at the anode. So when we compare the iodide to the water value, this value is more negative. So this is going to be happening at the anode. Okay, but now we're going to do the same thing for the reduction half reactions. Our lithium has an E value of negative 0.304. Oh, sorry, it was not negative. It was negative 3.04. Read that wrong. And now we're going to find the reaction where water is being reduced. So it's going to be gaining electrons. So if you look at our table and find the reaction where water is being reduced, it's H2O plus 2 electrons yields H2 gas plus 2 OH minus. Okay, and we see that the reduction potential value for this is going to be negative 0.41 volts. Our reduction is happening at the cathode. The cathode value has to be more positive. Okay, so between these two values, this is the more positive value. All right, so that's telling us the half reactions at the anode and the cathode. We can summarize it a little bit more neatly, I guess, down here. Draw one more line. So our anode half reaction is going to be 2I minus yields I2 plus 2 electrons. And our cathode half reaction is going to be H2O plus 2 electrons yields H2 plus 2 OH minus. Okay, but that's how we're deciding between the two. Okay, and our final type of example is going to be building on this electrolysis material. Okay, and that's going to be, how do we calculate numerically how much metal we can plate, for example? Okay, or how much time will it take to plate a certain amount of metal out in an electrolytic cell? So we're going to look at both types of questions here. Okay, so before we can really jump in and answer this question, we need to cover a few different things. One is the definition of Ampere. Okay, so 1 amp, or they have it shortened to a large A in this question, is going to be equal to 1 coulomb per second. Right? So when you see a term like this, 5.5 amps, that's going to equal 5.5 coulombs for every 1 second. All right? The other thing that you're going to need to know is the other thing you're going to need to be able to relate is the moles of electrons that are in the reaction you're focused on. The moles of electrons as it relates to the moles of the solid that you're looking to form. Okay? Because we're going to use Faraday's constant to link coulombs to moles of electrons. Okay, this link is going to be made by Faraday's constant. Okay, so without that link, without Faraday's constant, we're not going to be able to get from amperage into moles of electrons, which is going to allow us to get into moles of our gold in this case, and then figure out how much gold we can form. So what we want to start with here is our time. We know that we're going to be running this cell for 25 minutes. Okay. Amperage is in terms of coulombs per second. That means that I have to convert this minute value into seconds because that's the same time unit that's associated with the values that I was given here. So I know that in 1 minute there are 60 seconds. Okay, and I know that based on the amperage value that I was given, in every 1 second, that's going to be 5.5 coulombs. Right? Now I'm going to use Faraday's constant to go from coulombs to moles of electrons. Because Faraday's constant says that there are 96,485 coulombs in every 1 mole of electrons. And my reaction in particular has 3 moles of electrons in it for every 1 mole of gold. Now that I have my reaction in terms of moles of gold, now I can use the periodic table to figure out the mass of gold that was produced in this particular reaction. So 1 mole of gold is equal to 196.97 grams. Okay, I'm going to multiply every value that's on the top of my fraction bars. I'm going to divide by any value that's on the bottom of my fraction bars. Right, I end up with, rounding this to 2 significant figures, 5.6 grams of gold can be plated in 25 minutes with a 5.5 amp current. Okay. So again, now try the next one on your own before you watch me do it. Put it back up here so you can see it. You know, just pause the video and give it a whirl. Okay. So here we're kind of looking at almost the reverse question. Here they're telling us the amount of silver that we need to plate, and they want to know how long it will take for that to happen. Okay. So we're going to start with our mass value that we're looking for, that we're going to look to end up with, the 12 grams. So we're going to pull out our periodic table. And we're going to turn, you know, we want 12 grams of silver. Let's be real specific there. So we're going to use our periodic table to turn grams of silver into moles of silver. So that is 107.87. Okay. Once I've turned this gram value into moles of silver, now I can relate my moles of silver metal to the moles of my electrons. And it's a 1-to-1 ratio in this case, but I'm still going to write it in because I don't want to lose any of my units as I'm going through and making up my dimensional analysis. So now I have this in terms of moles of electrons. Okay, now I can get from moles of electrons into coulombs using Faraday's constant, which says that every 1 mole of electrons is 96,485 coulombs. Okay, and now I'm going to use my amperage. So remember, 3.0 amps is equal to 3.0 coulombs for every 1 second. All right, so my coulombs is going to go on the bottom in this case because I need to cancel it out. So it's going to be 3.0 coulombs in 1 second. I want a final time value that's in terms of minutes. So in my final conversion, seconds is going to have to go on the bottom and minutes will have to go up top. So in every 1 minute, there are 60 seconds. Okay, now again, I'm going to multiply every term that is on the top of my fraction bar, and I'm going to divide by any term that's on the bottom of the fraction bars. Okay, I end up with 59.63. I need to have this to 2 significant figures though. So 59.63 minutes is going to have to get rounded to 6.0 times 10 to the 1 minutes. All right, we can't report it as 60 because that would be ambiguous. All right, so that's most of the problems, most of the math types of problems that you're going to encounter in this chapter. If you have any questions about any of them, let one of us know.